lecture we study flexible manufacturing systems. In this lecture series we have seen some aspects of cellular manufacturing, just in time manufacturing and synchronous manufacturing. Now we move to the last part of this course, which is on flexible manufacturing systems. So flexible manufacturing systems is a manufacturing philosophy based on the concept of effectively controlling material flow through a network of versatile production stations using an efficient and versatile material handling and storage system. So this is one of the definitions of flexible manufacturing systems. Flexible manufacturing systems are called FMS in short. The important keywords here are control, effectively controlling material flow, network of versatile production stations, which is important, efficient and versatile material handling and storage systems. So the essential components of an FMS are effective material control, network of versatile production stations, efficient material handling systems and efficient material storage systems. So we integrate manufacturing, material handling and storage into a single system, and that is called a flexible manufacturing system. Another definition is FMS is a system that consists of numerous programmable machine tools connected by an automated material handling system. So in this definition the important keywords are numerous programmable tools, tools meaning machine tools, connected by, which talks of integrating machines with material handling system, and an automated material handling system. So three important things: programmable machine tools, connected or interlinked with the material handling system, and an automated material handling system. So all these three things come together to form a flexible manufacturing system. So if we combine both these definitions, we understand that an FMS consists of many programmable machine tools. So there is a lot of automation and computer usage. It is connected by an automated material handling system. So material handling is integrated and is part of the manufacturing system. FMSs have been there for about 25 to 30 years now, since the early 80s they have been there, and they provide a very efficient way to produce a very large volume, and they also have the ability to handle variety. Advantages of FMS are shorter lead times, shorter production lead times, ability to meet demand fluctuations, ability to handle both volume and variety, reduction in space and people, and obtaining better control due to automation. So 5 advantages are given here, and all these advantages are evident when we look at the definition, which talks of programmable machines connected by an automated material handling system. Again, as I mentioned, three things: programmable machines, automated material handling system, and they are connected. So when we do that, we will be able to have shorter lead times. Production lead times are smaller because most of the production is carried out by automatic machines. Material handling is an integral part of the manufacturing system, so automatically lead times are shorter. Lead times, production lead times depend on setup or changeover time, manufacturing time, transportation time, and good scheduling. So these 4 things are important to reduce lead times. In an FMS, setup times are smaller, largely because of what is called changeover flexibility or setup flexibility, about which we will see a little later. The ability to change over while production is happening, change over on some other, for some other product, or ability to set up another product while machining is happening on some other piece is called changeover flexibility. So, that reduces the changeover times. Machines are automated and have higher capabilities, and therefore, they reduce the manufacturing time. Material handling is integrated with the manufacturing, and therefore, time to retrieve and handle material, transport and retrieve material is reduced. And since the entire FMS is computer controlled, scheduling also becomes a part of the computerized control system, and therefore, good scheduling algorithms are used or good scheduling practices are followed, and therefore, all the 4 components of lead time are reduced in an FMS. So, lead times become shorter. Ability to meet demand fluctuations comes largely because of its ability to handle large volume as well as a certain amount of variety within the aggregated volume. So, FMSs have ability to meet demand fluctuations largely because of the capability of the machine tools which are automated. Reduction in space is expected, space and people, because in these type of manufacturing systems a single machine is capable of doing what 2 or 3 other semi-automatic or manual machines are capable of doing, and since there is a large extent of automation, people requirement is reduced, and be able to get better control due to automation happens simply because automation is able to provide a lot more production control. The manual intervention is very less and there is better production control due to automation. So, these are the advantages of flexible manufacturing systems. Flexible manufacturing systems are used largely in manufacturing electronic goods. One of the disadvantages, and in fact the main disadvantage of FMS, is that the initial installation costs and operation costs are very high, and it is also necessary to have enough volume to justify the use of FMS. Initial cost is very high largely because of the components of the FMS. A network of machines, a large set of programmable machine tools, each of them is extremely costly. Automated material handling and retrieval systems are costly. They can be rail guided or AGV, automated guided vehicles. Computerized control systems are costly to develop and implement, and therefore FMS is a costly proposition. Size is small, but the cost is very high. And secondly, in order to have an FMS in place, the organization should justify it through large volumes. So, if the volumes are large, then organizations go for FMSs, but then the disadvantage is that the organization should have enough volume to justify the use of FMS. Sometimes FMSs are installed and then there is an effort to increase the production volumes. FMSs are classified into 3 types: flexible manufacturing cell, flexible manufacturing system, and flexible manufacturing line. So, FMC, FMS and FML. All these are essentially terminologies. Flexible manufacturing cell by definition is like a single cell, as in cellular manufacturing, having 3 or 4 different types of automated machines coming together, and all the parts are produced within the cell and the parts are made and sent to customer or to assembly. Flexible manufacturing system by definition is a collection of flexible manufacturing cells, at least 2 or more flexible manufacturing cells, each cell having a certain number of automated machines as well as a computer controlled material storage system and material handling system, more than one cell. parts are made in different cells, can be assembled or sent to the customer. Except for the size and aggregate volume, FMC and FMS are the same. Flexible manufacturing line is like a production line. It is like a flexible manufacturing cell, but it handles more volume and very few products compared to a flexible manufacturing cell. So, if the volumes are very high, or if a cell is required to make only one product, then it becomes a flexible manufacturing line. If it makes more than one, then it becomes a flexible manufacturing cell with a little more variety, and a collection of flexible manufacturing cells make a flexible manufacturing system. So, that is written here. FMCs have high flexibility, handle less volume, while FML have less flexibility, but can handle very large volumes. So, depending on the volume, we call it an FML or FMC, depending on both volume and variety. Now, since the system is called as a flexible manufacturing system, it has to be flexible. So, we try and define what are the types of flexibilities that are part of a flexible manufacturing system. Several flexibilities exist. Now, we concentrate on 5 important aspects of flexibilities, and these 5 flexibilities are operation flexibility, part flexibility, changeover flexibility, routing flexibility, path flexibility. So, there are 5 flexibilities that are defined, and each of these are explained as follows. Operation flexibility is the ability to perform more than one operation on a given part type. So, the given part type is fixed, it is set up on the machine, but then we have multiple tools working on the part, and that is called operation flexibility. Due to operation flexibility, the time taken to produce reduces significantly. Many things change. Normally, the time taken as far as the computations are concerned is the sum of all the operation times, but when the FMS has operation flexibility and can do 2 operations at the same time on the piece, then the time is the maximum of the 2 and not the sum of the 2. So, the very approach or the way to calculating the time taken changes. So, operation flexibility brings in a completely new perspective with respect to manufacturing. Part flexibility is the ability to perform operations on more than one part at a time. So, there are 2 parts, and then there are tools that come and work on both the parts. Now, this again changes the way one does computations and scheduling. Time taken for a batch is always the batch size into unit processing time plus changeover time. Now, if it can do 2 parts at a time or 3 parts at a time, then we have to do batch size divided by 2 into unit processing time. So, as a result of both, we find that the time taken to process reduces significantly. Then we have changeover flexibility. Changeover flexibility is the ability to change over from one part to another in negligible changeover times in parallel when operation is performed on another piece. So, changeover flexibility is like this. There could be 2 tables. On one table, an operation or some manufacturing is happening on a piece. On the other table, we are able to change over from one piece to another, and once this is over, they can index, and the one that is already fixed or it is already set up on the machine, the manufacturing happens on that. The one on which the manufacturing is over is removed and another piece is brought in. Now, changeover time happens in parallel when manufacturing or production is happening on another piece. So, it is the ability to change over from one part to another in very small or negligible changeover times. Many times these changeovers also happen with the help of robots or with the help of computer controlled systems, and they happen very fast. So, once again the very definition of time to produce will change, because usually the time on a batch is the changeover time plus batch size into unit processing time. If we bring all the 3 together, the changeover time becomes negligible because it can be done in parallel while something else is happening. Due to operation flexibility, maximum time of the operations is now taken. Due to part flexibility, if 2 parts can be done at the same time, the batch size is divided by 2 and all the 3 components of the processing time of the batch reduces. Therefore, the time taken to produce reduces considerably in the case of a flexible manufacturing system. Routing flexibility means that a particular part can be delivered to any one of the number of alternate stations. So, if we have a flexible manufacturing cell with, let us say, 4 workstations and there is a particular part which requires a certain operation and more than one can handle it. In a normal conventional manufacturing system, the routing is done before the manufacturing begins. Many times the routing is predetermined and fixed, and then we say it will follow a particular route till all the operations are over. Now, because we have routing flexibility, dynamically as and when the part is coming, a machine amongst the alternate machines can be chosen, and since the entire thing is computer controlled, it is linked to the material handling system and the part is quickly taken by the material handling system to the machine to which it is assigned. So, routing flexibility gives the advantage of higher utilization of the machines as well as reduced waiting times, because that particular machine could be working, could be busy, while there could be another machine that is idle and one could go to that machine. And since all these are controlled by computer, there is no disruption, there is no change that affects the production, and things are done much faster. So, routing flexibility gives the advantage of higher utilization and less waiting time for all the parts. Another advantage is that if we compare this with a cellular manufacturing system or a cell within a cellular manufacturing system, it is quite unlikely that for a particular operation we could have more than one machine in the cell, because the cell invariably contains a set of functionally dissimilar machines. Whereas in a flexible manufacturing system, if there are 3 or 4 workstations, it is quite likely that more than one workstation can handle every operation, because most of these workstations are so versatile that they are capable of handling a large number of operations, unlike machines in a manufacturing cell as in cellular manufacturing system. So, routing flexibility is something unique to FMS and helps in reducing the time to produce. Path flexibility results from the existence of more than one possible path from a specified origin to a specified destination. We mentioned that within a cell or within a flexible manufacturing cell, FMC, if it has multiple workstations, parts move from one workstation to another. We also mentioned that material handling or transportation within the FMC is automated using rail guided vehicles or using AGVs. So, if a part has to go from one particular machine to another machine, in a normal traditional system only one route is specified. Because this entire system is computer controlled, we could have alternate routes and the system will have the ability to choose the alternate routes. For example, we could think of these 4 machines within an FMC, and we could have now let us assume these are the 4 machines. Now, let us say one particular part is over here and it has to go to M4. Now, it could take either from M2 this way to M4 or it could go this way to M4, or it could come this way and go to M4. So, this is an example of having alternate paths between M2 and M4. So, if the original path is this and for some reason there is something happening here, then it may not be able to take this path. Now, this path will now be changed to either this path or the other path. So, this is an example of path flexibility. So, we have seen 5 types of flexibilities, and these flexibilities, all of them essentially help in minimizing the delay. As I mentioned earlier, the time taken to produce is the time to set up or change over from one part to another, time taken to actually produce and manufacture or for the operations, time taken for material handling, transportation and retrieval, and 4 time taken or time taken if machines are idle due to scheduling issues. Now, once again, if we look at all these 4 times from the point of view of the flexibilities that we talk about, changeover flexibility reduces the changeover time. Changeovers are also quick because they sometimes are computer controlled and robot controlled. So, changeover times are smaller. Changeover flexibility, which is the ability to do changeover on one side when operations are carried out on the other, reduces the changeover time from the calculations because it is done in parallel. So, changeover times are reduced. The actual time to machine or carry out the operations reduces due to operation flexibility and part flexibility. Operation flexibility has the ability to perform more than one operation, so it could be halved. Part flexibility is more than one part, so the batch size effectively reduces for the purpose of calculation, while routing flexibility and path flexibility reduces the delay in transportation, material handling, etc. By changing the route and utilizing a machine that is free, the scheduling delays are minimized. So, routing flexibility helps in reducing the delay and idleness due to scheduling, and path flexibility reduces the time taken to transport by considering alternate paths from one machine to another. So, all these types of flexibilities also help a flexible manufacturing system to cut down the first important gain which I mentioned is shorter lead times. So, lead times are shorter due to these flexibilities which are part of the flexible manufacturing system. Now, we get into some aspects of modeling in flexible manufacturing systems. So, several researchers worked on different types of problems in flexible manufacturing. Some of these problems are unique to flexible manufacturing. While the problems are unique to flexible manufacturing, the methodologies used to solve them are new in some cases and traditional in some other cases. So, we will look at some interesting production planning problems in the context of FMS, and we will look at them in detail through numerical examples, and we will also try and solve them using newer methodologies as well as existing methodologies. So, one of the important work in the area of flexible manufacturing is by Steck, who gave 5 production planning problems in flexible manufacturing. She defined 5 important problems which a production planner should consider while implementing a flexible manufacturing system. So, the first one is called the part selection problem, second one is called the machine grouping problem, third is the production ratio problem, fourth is the resource allocation problem, and the fifth is tool and machine tool allocation problem are the 5 important production planning problems in FMS. Now, what is the part selection problem? Part selection problem talks about choosing that subset of parts which are going to be made in the FMS. Now, we are going to make an assumption here that the entire factory is not going to operate on the FMS mode. we are going to assume that a certain portion of the factory is going to operate on the FMS mode. If the entire factory is going to operate on the FMS mode, then the part selection problem does not exist, because all parts have to be made in the FMS. So, we are going to assume that some parts are going to be made in the FMS, while some parts are not going to be made in the FMS. So, amongst these parts which are going to be made in the factory, which are the ones that are going to be made in the FMS is the part selection problem. Now, we look at the part selection problem in detail through a numerical example, which we will try to solve. Second one is called the machine grouping problem, which is to group machines such that any machine in a group can handle all the jobs that other machines in the group can process. So, in this case, the author is talking about grouping similar machines into one group, like a functional or a departmental kind of a system, except that the number of such machines will be very small, and these machine groups will also be located physically close to each other and not very far away from each other. Flexible manufacturing system reduces the size of the plant considerably. There are fewer machines, each machine is extremely versatile and fast and can handle a lot of variety, fewer machines, and they are all connected by a material handling system. So, in principle they cannot be very far away from each other, because it will be extremely expensive to transport from and to these machines which are very far away from each other. So, they are very close to each other, physically located, and space required is very less. So, a machine grouping problem is where the machines are grouped such that all the machines in the group can handle all the jobs which other machines can process. So, that if there are a set of jobs that are allocated to these groups of machines, now which job will go to which machine is called a loading problem, which we will see much later. Loading problem with additional constraints we will see later, but it helps in the machine loading problem where groups of similar machines are made. Third problem is called the production ratio problem, to decide the ratios in which parts chosen in one can be made. Now, there is a certain time available in the FMS, and that time has to be used to produce the parts that are chosen in problem number 1. So, what percentage of the demand of these parts are going to be met by the FMS? So, that is a production ratio problem. Resource allocation problem, to allocate limited number of pallets and fixtures to the selected part types. FMS contains pallets and fixtures, tools, these are all sometimes scarce resources. We do not have too many tools that are available, but the same we might have just one tool of a particular type, and that tool now has to be scheduled. It can be fixed on different machines at different points in time to handle different parts. So, resource allocation problem essentially allocates all the scarce resources to the machines over time. So, there is an allocation and there could also be a scheduling, which actually comes in the fifth problem, to allocate operations and tools to machines to meet stated objectives. Making a part would involve a set of operations, and each operation would require a set of tools. Now, it is not necessary that all the operations go to the same machine. So, if there are more than one machine in a group, then some operations can go to machine 1, some operations can go to machine 2. Now, this helps in balancing the loads, which essentially brings out, when we are producing a large batch, it brings out items quickly. So, there is a load balancing objective where when operations are allocated to, when jobs are allocated to different machines and operations are allocated to different machines. So, sometimes the entire job is allocated to one machine, where we do allocation of jobs to machines. Sometimes the jobs contain several operations, and some operations are carried out in one machine, while some other operations are carried out in some other machine. Now, when certain operations are allocated to certain machines, then the corresponding tools have to be allocated. So, there would also be constraints about the availability of these tools. So, these tools are to be allocated to various machines and scheduled over a period of time, so that the tools can be used from one machine to another, so that all these operations can be carried out. So, all these are production planning problems in the context of flexible manufacturing systems. So, we will now look at some of these problems in a little more detail. So, the first problem that we will look at from a modeling perspective is called the part selection problem. So, choose the set of parts that maximizes profits subject to time availability constraints. So, consider 4 parts that are made in an FMS. The profits are 12, 10, 8 and 9, and the time required are 20, 16, 15 and 12. Available time is 45. Find the parts that have to be made or that can be made in the FMS is the first problem that we will take from a modeling perspective. So, we look at 4 parts. The profits are 12, 10, 8 and 9. And the times are 20, 16, 15 and 12. Now, we have to find out whether which of the 4 parts are to be made on the FMS. The reason is the time available on the FMS is 45, whereas the time required on all the 4 put together exceeds 45. So, all of them cannot be made. So, which are the ones that are going to be made? So, we define x1. So, x1 plus 16 x2 plus 15 x3 plus 12 x4. So, xj equal to 1 if part j is going to be made in the FMS, xj equal to 0 otherwise. So, the profit will now become 20 x1 plus 10 x2 plus 8 x3 plus 9 x4, which is to be maximized subject to a single constraint, and xj is binary, it is either 0 or 1. Now, this problem is called a binary knapsack problem. It is called a binary knapsack problem. It is like having a knapsack with volume equal to 45, and there are 4 items. Each item volume is 20, 16, 15 and 12. Now, which are the items I can put into the bag such that the bag is able to hold the items. So, x equal to 1 if I choose that item, x equal to 0 if I do not choose that item. It is binary because there is only one item available of each type. So, I either take it and put it into the bag or I leave it. Now, from a operations research perspective, it is a simple integer programming problem, binary IP with a one constraint and a maximization objective. So, this problem can be solved comfortably up to a reasonable size, even though very theoretically this problem is a difficult problem. Up to a reasonable size it can be solved extremely comfortably. So, we could simply solve this problem using a simple solver to get a solution. Now, the optimum solution is y1 equal to y4, y1 equal to y2 equal to y4 equal to 1. Now, essentially so to begin with, we can actually directly solve this problem as an IP, there is no difficulty at all. So, the solution is 9, 10 and 8, 10, 8 and 9, these are the solutions that make up. So, we can actually solve this with the x itself. I will later explain why we define the y's, but we can solve it with the x itself. So, this would give us 16 plus 15 is 31 plus 12 43. So, 43 units is used, and the profit will be 10 plus 8 18 plus 9 27 with x2 equal to x3 equal to x4 equal to 1 is the optimum solution if it were solved using a particular solver. But if we do not have a solver and if we wish to solve it optimally, then we could do what is called a branch and bound algorithm. Which I will describe now. Now this is something which we have done earlier also. What we do in this case is to find out the ratio of the objective function to the constraint. Whenever you have a single constraint integer programming, either binary or integer, you find out the ratios. So the 4 ratios are 12 by 20, 10 by 16, 8 by 15 and 9 by 12. So these ratios are 12 by 20 is 0.6, 6 by 10 which is 0.6, 10 by 16 is 0, 16 6 are 96, 40, 16 2s are 32, 0.625, 8 by 15 is 0, 0.80, 5s are 75, 50, 0.533 and 9 by 12 is 0.75. Now arrange these coefficients or arrange the variables in the decreasing order of coefficients. So this will become 1, the highest coefficient, this will become 2, this will become 3 and this will become 4. Now rewrite the problem by renaming the variables. So this will become y1, this will become y2, this will become y3 and this will become y4. So x4 will become y1, x2 will become y2, x1 will become y3 and x3 will become y4. Therefore the problem will take the form that is given in the slide, which is to maximize 9y1 plus 10y2 plus 12y3 plus 8y4 subject to 12y1 plus 16y2 plus 20y3 plus 15y4 less than or equal to 45. Now yj is binary. Now the reason for doing this is for renaming the variables and redefining the variables in the decreasing order of Cj by Aj as it is called, or Cj by Tj as it is called in this case, is if we now solve an LP by leaving out this, a single constraint LP will have only one variable in the solution, and because the variables are already sorted in the decreasing order of Cj by Tj, the one with the highest Cj by Tj or the leftmost variable is the one that will be in the solution. For that reason the variables are rearranged, so that when we solve an LP of it, now this is a binary IP because of the 0 1, it is not a linear programming problem. If we solve a linear programming problem out of it, then such a linear programming problem, the variable in the solution will be the leftmost variable that we have. For that reason this is being done. This also helps us to develop a branch and bound algorithm, which we will see now. We start the branch and bound algorithm by solving the linear programming problem first. So when we solve an LP relaxation of it. Now this is solving Yj greater than or equal to 0 if we solve an LP relaxation. Now this is a single constrained LP, therefore only one variable will be in the solution, and we have already sorted the variables in the decreasing order of Cj by Tj. So leftmost variable will be in the solution. So this would give us a solution y1 is equal to 45 by 12 and z is equal to 9 into 45 by 12, which is 45 into 3 by 4, which is 135 by 4, 12, 15, 4 3s are 12, 30, 33.75. So this would give us a solution with 33.75. It is a maximization problem, therefore linear programming will be an upper bound, LP relaxation will be an upper bound to the binary or IP optimum. So this would tell us that the optimum is less than or equal to 33, it cannot be more than 33 or it cannot be more than 34. So now we proceed and create two nodes where y1 is equal to 1 and y1 is equal to 0. So this will be y1 is equal to 1, this will be y1 is equal to 0. So when we force y1 equal to 1, then we are making this, so this variable comes out of the solution. 12 units are already used, so now what is available is 33, because this 12 is already used in y1. So when y1 equal to 1, the corresponding LP solution will now become y2 equal to 45 by 16. So this solution will be y2 equal to 45 by 16 and z is equal to 10 into 45 by 16 5 into 45 by 8 225 by 8 8 2s are 16 65 8 8s are 64 y1 equal to 1 means 12 units are already used up, so only 33 units are available. So this will give a solution y2 equal to 33 by 16 and z is equal to 330 by 16, which is 165 by 8, which is 20.5 by 8, 50, 8 6 are 48, 20, 20.625 plus another 9 because y1 is equal to 1. So upper bound is 29.625. Now you see that it has come down from 33.75 to 29.625. Now y1 equal to 0 would give us a bound. Now y1 is equal to 0. Now y1 variable is out, but all the 45 resources are available. So the solution will be y2 equal to 45 by 16 and z is equal to 450 by 16, which is 225 by 8, 8 2s are 16, 65 8s are 64, 10 1, 28.125. So this would give us y2 is equal to 45 by 16 and z is equal to 28.125. Now we branch from the node that has the higher value of this. So now y2 is equal to 1 and y2 is equal to 0, y2 equal to 1, y2 equal to 0. So y1 equal to 1, y2 equal to 1 takes away 12 plus 16, 28 units. So 17 units are available here. So Y3 will be 17 by 20, Z is equal to 12 into 17 by 20, which is 68 by 5, 51 by 5, which is 10.2 plus 19. So you get 29.2. The other one will now become y1 equal to 1, y2 equal to 0. So we are operating here. Y1 equal to 1 takes away 12, so 33 units are remaining. So y3 will become 33 by 20 and Z is equal to 12 into 33 by 20, which is 99 by 5, which is 19.8, plus y1 is 28.8. So this will become 28.8. So now again y3 can take 0 or 1. So y3 is equal to 1, y3 equal to 0. So y1 equal to 1, y2 equal to 1, y3 equal to 1 is 12 plus 16, 28 plus 20, 48 is infeasible. Now 16 plus 12, 28 plus 15, 43 is feasible. So this, when y3 equal to 0, we come to the last variable, which is y4. So y4 can take 0 or 1. So y1 equal to 1, y2 equal to 1 takes away 28 units, 17 units are available. So that can give us y4 equal to 1 and Z is equal to 9 plus 10, 19 plus 8, 27, which is feasible. So 27, which is feasible to this problem. Now we have to go back to the other things and branch. So when we branch from here, we create two nodes, which is y3 equal to 1 and y3 equal to 0. So now when y3 is equal to 1, y1 is 1, y3 is 1, y2 is 0, y1 is 1, y3 is 1, y2 is 0. So we have 12 plus 20, 32 that is consumed. Y3 is 1, 32 is consumed. So automatically y4 will have to be 0. So y4 will be 0. So this will give a feasible solution, y1 equal to 1, y3 equal to 1 with 12 plus 9, z equal to 21. And since it is less than 27, this is fathomed and this is not going to help. The fourth one is y1 equal to 1, y2 equal to 0, y3 equal to 0 will give us enough resource to do y4. So y4 equal to 1 and this will give us z equal to 17, which is again fathomed. So right now we have a solution with z equal to 27, which is our best solution, but the algorithm does not stop, because we also have to branch from this side, because from here the upper bound is 28.125. So we could get a solution with 28, because these are all integers and these are also integer values, binary. So the objective function value at the optimum will be an integer. So we have to proceed from this, because there is still a chance of getting a solution with 28, which we have to explore. Right now the best value is 27. Now we will continue the branch and bound algorithm and try to get to the optimum solution in the next lecture.